Okay, in this presentation, I'm going to give an overview of analog signals and transforming analog signals into digital signals. Because in essence, that's what our instruments do that we're going to work with this semester, is they take an analog signal, convert it to a digital signal, and then we process those data. So I'm going to give a big overview of this. I have some other detail or videos that have more granular level detail for these different topics, and you can go and watch those as well. So this is more just an overview. All right, so why do we need digital signals? Well, as I said, our movements are analog signals. As I flex and extend my elbow, that's happening analogically, and I'm going to explain what that means in just a bit. Computers work in the digital world and digital data. They have very discrete data points that we work with. The sensors that we use, the instruments that we use in sport performance testing are in essence taking those analog movements, flexions, extensions, and transforming those movements into digital numbers. All right, so what is an analog signal? Well, an analog signal is anything that is a continuous time function. So as I flex and extend my elbow, this is continuous. Or if you look at an analog clock, this is supposed to be an analog clock. And you see these cartoons here. These are from notes that I have that you can get access to as well. And so there's more explaining about these figures in other videos. But an analog clock is one that has hour hand and a minute hand and maybe a second hand as well. And that's a continuous time function or continuous time type of clock. Whereas, and there's infinite values, okay? It's continuous time. A digital signal has discrete time and discrete values. So a digital clock, 3:05, all right? The next number would be 3:06. The next number would be 3:07. Whereas an analog signal is continuous time, and there is not those discrete intervals. So an analog to digital board or an analog to digital instrument takes that analog signal and transforms that analog signal into a digital signal. And so every instrument that we use has some type of analog to digital operation. And I say analog to digital board because that's typically what we use, but there are other devices like we use digitizing in cameras, and we could do some other things other than use a electronic A to D board. But an A to D board, what does it do? It simply samples the analog signal, quantifies the signal, and then outputs digital data to the computer, and then the computer has the data set, and that's what we are actually analyzing. And there's different types of A to D boards. And typically we describe the A to D boards based upon the number of bits that it has. Now, a bit is a single representation of memory. And if we have, and a bit can either be a 0 or a 1, it's binary. And we can have an A to D boards with only 3 bits, and we can have A to D boards with 64 bits. Again, there's another presentation I have that goes into much more detail on this. But in essence, a to D board with fewer bits has fewer discrete values. A to D board with lots of bits, a 64-bit A to D board, has lots, 2 to the 64th values that it can represent. So if we take a voltage range, and I'll explain this more in other videos, but if we take a voltage range of 10 volts and we divide those 10 volts into discrete values from a 3-bit A to D board, we only have 8 divisions. Whereas a 64-bit A to D board has 2 raised to the 64 division. So we divide that 10 volts into lots of small little increments. So we have lots more resolution of being able to detect different voltages. So in essence, if you're buying an instrument, you do want to often ask the seller, well, what's the A to D board resolution? And they may say, well, this is a 3-bit A to D board, or it's a 64-bit A to D board, or what have you. Back in my day, where I was doing my PhD work in the 90s, 64-bit A to D boards were super expensive. And so often we were using A to D boards with lower number of bits simply because of a cost issue. But today, it's not too hard to come across a 64-bit A to D board. So what now? We have an A to D board, which converts a signal, analog signal, to a digital format. Well, now we also have to talk about how quickly we are sampling data. And so we use this term sampling rate. FS is our symbol for that. And we typically talk about samples per second, which would be units of hertz. And hertz is anything per second. And so we'll use hertz in a wide variety of ways throughout the semester. But from a A to D board, from a sampling perspective, sample rate is talked about in terms of samples per second. And so we may say the sample rate of this instrument was 10 hertz, 100 hertz, 1,000 hertz, whatever it is. That means 1,000 samples every second for a 1,000 hertz sample rate. And a lot of our instruments have different sample rates that can be selected. Higher sample rate covers more detail, but requires more storage of data. Too low of a sample rate, you end up actually losing some information and may actually get some errors in your representation of the analog signal. All right, so when we are selecting a sample rate, we need to follow what's called the sampling theorem. And the sampling theorem says we need to sample an analog signal at a rate greater than twice the highest frequency that you want to detect. All right, I know that's a lot. There's a lot of math built into this sampling theorem. But if we do this, we actually successfully reproduce the analog signal in the digital world. All right, so what does this mean? This means that if I want to detect a signal that is 1 hertz, I need to be able to sample at a rate greater than 1 hertz. So I have to sample at something like 2 hertz. All right, or it has to be greater than twice the highest frequency we want to detect. So if I have a 1 hertz signal, I need to sample at something greater than 2 hertz. So 2.1 hertz or 2.5 hertz or 3 hertz or 5 hertz or 10 hertz. Any of those will actually allow me to reproduce the analog signal successfully. If I sample at 1 hertz, for example, if I have this sine wave, and here's amplitude of the sine wave on the y-axis and time on the x-axis, if I only sample this 1 hertz second every 1 second, I'd be sampling here, and I'd be sampling all the way over here. And I'd have 2 dots, and there'd be no way for me to reproduce this sine wave based upon just those 2 values. And so we need additional values, and once we have those additional values, then we can reproduce the analog signal. Aliasing happens when we sample at too low of a rate. We see this all the time. If you watch someone biking and you record them via a video camera, which samples at roughly 30 frames per second, and you're watching someone bike, it actually looks like the wheel spinning backwards, right? You've seen that, I'm sure. Well, that's an aliasing problem. That means that our sample rate is not high enough to actually detect the spinning of the wheel, because the spinning of the wheel is at a higher frequency than what the camera can detect at 30 hertz. And so aliasing as high frequencies appear as low frequencies, and it ultimately can create misleading data. This has shown up in research when we are using devices, sometimes off the shelf, which do not have an adequate sample rate. For example, I was testing out an instrument that measured muscle activity, and the data just weren't coming out as expected. I contacted the manufacturer, and the manufacturer, I asked what the sample rate of the device was, and he told me it was 50 hertz. That we know is too low of a sample rate to collect muscle activity. Later on in the semester, we'll actually talk about electromyography and some adequate sample rates to use for electromyography, but 50 hertz is too low. And it ends up introducing error in the signal, just like the wheel looking like it's spinning backwards on the camera. We know the wheel's not spinning backwards. And likewise, in sampling EMG at too low of a rate, we end up getting errors that way. So I've introduced a sine wave, and that it takes us into different ways to look at the data when we actually have it on the computer. And there's two main domains that we look at the data. One is the time domain, and the other is the frequency domain. The time domain is what we're used to seeing. That is, we take a data point and we plot it across time. And so if I even go back to some of the previous slides where I showed the sine wave, I had amplitude of the sine wave on the y-axis, I had time on the x-axis. That's a time domain. And we're all comfortable, most likely, seeing data in that sense. A frequency domain analysis is where we have frequency on the x-axis. So here, this is a time domain plot. I have magnitude on the y-axis and time on the x-axis. Magnitude on the y-axis, time on the x-axis. And whereas the frequency domain analysis, we have magnitude on the y-axis and frequency on the x-axis. And this frequency represents the frequency of different sine waves. A 1 hertz sine wave, a 2 hertz sine wave, a 3 hertz, and so forth. And then the amplitude represents the magnitude or the amplitude of that sine wave. And so we get signals, or we get a frequency representation that looks something like this, where you have magnitude down here, and we have frequency on the x-axis, and then all these little dots represents all the signal, all the sine wave amplitudes that ultimately make up an analog signal. So let me explain that a little bit more. But let me get to sine wave as a building block for frequency domain analysis. In essence, the way that we approach a frequency domain analysis is all signals can be represented by a summation of a lot of different sine waves. And each sine wave has a frequency and has an amplitude. And the complex signals that we look like can be broken down to a series of different sine waves. And let me explain that in just a bit. So a sine wave is, there's some math behind it. I'm sure you've had this in some math class or maybe a physics class, but this is a representation of a sine wave. We have amplitude on the y-axis, time on the x-axis, and a sine wave is this very characteristic curve. And we have an amplitude and we have a frequency. And sorry, my picture is in the way of these things here, but the time to complete one sine wave will tell us the frequency of the sine wave. A fast Fourier transformation will take our time domain data and it will transform that time domain into a frequency domain analysis or signal. What do I mean by that? Well, what we're doing in a fast Fourier transformation is we're taking this signal here, whatever it is. This is now a digital signal, but we're taking that and we're saying, you know what? If I lay out enough different sine waves, I actually can reproduce this signal. And if I add up all those different sine waves. And what this plot over here tells me is all the different sine waves that I need to represent this signal. I need a sine wave with this amplitude at this frequency. I need a sine wave with this amplitude at this frequency, this amplitude, this frequency, this amplitude. And if I overlay all those different sine waves, I add them all up, I will get this signal. All right. So now I have two ways of looking at the same signal, looking at the signal in the time domain with time on the x-axis and in the frequency domain, which is frequency on the x-axis. This fast Fourier transformation, this frequency analysis is heavily used in biomechanics, and as we talk about the difference in different instruments, we'll talk more about this. And this leads to smoothing of data. And in smoothing of data, what we're trying to do is remove noise that is within the signal and we're trying to remove the noise, but we're trying to retain the actual signal that we want to represent. In essence, as we start recording data, we'll learn that every signal will have some type of noise. And noise is defined as the part of the recorded data set that is not representative of the signal. So it enters into the signal some way. For example, a movement artifact or electronic interference. So a movement artifact would be, if I'm using EMG again as an example, if I'm trying to measure muscle activity and my sensor starts moving, my sensor can actually measure some of that movement as opposed to measure the electrical signal of the muscle. So that's a movement artifact, that's movement noise that enters into the signal that's actually being recorded. We can also get interference from the electronic wilderness that we live in. Again, using EMG as an example, I've done studies where someone's on a treadmill and we're measuring the electrical activity of the muscle by sensors on the skin, and the person grabs the treadmill and actually ends up being an antenna to bring in electronic noise from outside the body, and that would enter into the electromyography signal. And it's a noise, it's electronic noise, it's an interference. And so we have to deal with this issue when we are recording data, and we always have to recognize that sometimes our data are inflicted by noise that interferes with our ability to understand the analog signal. So identifying noise is not always easy. It's hard. I gave you a couple examples where it seems easy and you can detect it, but it's not always that clear. To identify noise, what we will typically do is we will take the data, put it into the frequency domain, and then we will look for frequencies that are not humanly possible. So for example, if we're looking at a running data set and we record some data electronically, and we see a signal that has 500 hertz magnitude, sine waves that are contributing at 500 hertz. We're not moving at 500 hertz. That's 500 times per second. It's way too high, and so that would be a way to try to detect noise. And likewise, if we're doing something with EMG, we know the base frequency for the types of signals that we see in muscle activity. We can identify movement artifact as being a low frequency. That's in the frequency domain analysis. And so this is going back to the frequency domain analysis. Why it becomes so important is to try to identify sources of noise or how much noise is within our signal. But there's always an overlap between real signal, most of the time, there's an overlap between real signal and noise. And so smoothing our data is always a balance between retaining a signal and removing noise. This is an important concept to understand because a lot of instruments that we buy to measure human movement, there may be proprietary processing that involves smoothing the signal, and it may not be really clear to the user until you start trying to ask some questions. I had that happen to me where I was using an instrument and the signal was coming out way too smooth than expected. I contacted the manufacturer and they said, oh yeah, we actually do some smoothing of the signal before you actually see it. And I was like, well, tell me more about that smoothing routine. And they didn't actually have the details of that smoothing routine that they could disclose to me. So now I'm dealing with an instrument that is making some decisions on processing the signal without my input. And so that as a researcher, we want to try to minimize a black box type of approach to processing data. We want to try to get our raw data as much as possible and then actually process the data and smooth the data using our routines and our algorithms. There's lots of different techniques to smoothing data. And these are some of them and the most common ones. And we'll talk about them as we start talking about processing data. Once we have the data, we have this 1,000 hertz signal. We've kind of calculated 1,000 data points every second. Well, now we need to take those data points and then process them in some way, and often that involves smoothing. Sometimes it's a moving average. We take some subset of the data. Maybe we take half a second worth of data. We average that half a second data to create a new data point, and then we shift the data, that window, over one data point and calculate a new average, and then new average, and new average. Create a new data set by averaging a subset of data. And there's different ways to do that. And we'll most likely touch on that during the course of the semester. There's a line of best fit. Fit the data with some type of polynomial, first order, second order, third order, what have you, and then recreate the signal from that line of best fit. There's a low pass filter. These get a little confusing, but it's once you go through them a little bit. But the low pass, the high pass, and band pass and notch filter are all done within the frequency domain. A low-pass filter is where frequencies below a specified cutoff frequency are passed through the filter. So I want those frequencies to be retained for analysis. We get rid of signal above a cutoff frequency. A high-pass filter, frequencies above a specified cutoff frequency are passed through the filter. Now, bandpass filter is where amplitudes of the bandpass of a frequency are unchanged. So I give a low frequency, I give a higher frequency, and I want that band of frequencies to pass through for analysis. And a notch filter is just the opposite of that. The amplitudes of a bandpass frequencies are changed. This happens in EMG. I mentioned the noise from grabbing onto a treadmill rails. That noise ended up being a 60 hertz signal. 60 hertz, well, that's our electronic world where we plug into an outlet. And so we were able to create a notch filter to take that 60 hertz signal out of the EMG signal, and then we retain the actual usable part of the digital data. So let's put it all together. Well, we have an analog signal, which is a continuous time function, a digital signal, which is discrete time intervals, and we use A to D boards to convert our analog signal to digital. We have to have an appropriate sampling rate following the sampling theorem, which is we need to sample at a rate greater than twice the highest frequency we want to detect. If we don't do that, we actually run into equalicy problems, which is errors in the signal. And then our analysis, we have time domain and we have frequency domain analyses that ultimately lead into smoothing techniques. Why is this important? Why does it matter? Well, this is all going to be about the learning instruments, how to collect data, how to process data. So when we're collecting data, we want to use an appropriate A to D board. We want to use an appropriate sample rate. When we process data, we want to smooth data appropriately. We want to possibly do an analysis in the time domain, maybe in the frequency domain. And this is true for all the instruments that we're going to work, whether it's motion capture, force platforms, EMG, electromyography, ECG, electrocardiograph, any wearable sensors. It's all taking analog signals, trying to create a digital signal through these processes. Okay, so that's a big overview. I hope that's helpful. If you want more detail, there's other videos to watch. All right, thanks so much.